Everyone. Oh, okay, so yes, to all the ones online, we remind you that this will be recorded and maybe even published on YouTube. So be nice to Jean-Paul. It's a great pleasure for me to introduce a very old friend.
Not at all.
So we know each other since the DEVA, which was the former Master 2 in Paris. And we did our PhD at the same time in the same lab, Rue Laumont, Laboratoire de Physique. And after we split it, he went to the US for a postdoc in Washington at NIST, but financed by Ron Poulenc at the time and supervised by Bernard Caban. After that, he was hired by CNRS in a lab in Lyon on polymers, which became, after some mergers, the Institut Materiaux Polymères. He was there for 10 years. And in 2004, he joined the lab, the Rhodia Cranberry lab, where I was just for 1 year before him, right the year before him. So we spent 2 years together in that lab, and you spent 4 years over there. And after that period in his Rhodia lab, he came back to France, but at Bordeaux, where he is since then. So, Jean-Paul, the floor is yours.
Thank you, Pierre. Thank you for the introduction. So thank you very much for the invitation, Pierre and Thierry. I should say that this was my first time ever in Strasbourg, and I did enjoy it a lot. Actually, the city is wonderful, and biking here it's just a pleasure compared to Bordeaux, where it's kind of dangerous to bike. So today I will talk about polymer films, the effect of confinement, and actually in French I wrote a subtitle "Confinement chamboule aussi les polymères," because actually this is a long story. But, we wrote the last. I mean, we tried to write the last paper really during the lockout. I mean, in France. So. I remember I was confined as well with my family, so the density was kind of high in the house with pretty much no mobility at all. So this was kind of funny. I was like Michael. I would like to say also that this is typically a background study. By background, I mean that we made it with my colleagues over the years, but without any funding, and we did it when we had time, actually. But it was funny and interesting, so I decided actually to stop here rather than to talk about something else. Though the something else, I will just 2 slides to show you what we are doing also. We are interested in self-assembly in general, and also on how the pathway of substrate choose will impact at the end of the structure we want to generate. And here, typically, recently, we have been putting forward with my colleague Christophe Chat from LCPO, with the help of Flavia, the PhD student, a new way to assemble, self-assemble bilayers. Block Copolymers by layers, basically in 2 steps on any kind of substrate, typically macroscopic substrate, but also colloidal object, porous material. Here, obviously, the first steps is adsorption, and the second step, you add water. And the way you add water, you have to be careful. You will generate different structure, and at the end we get what we want, the bilayer of the surface. So this is typically what we are doing currently, and we are also interested since many years on co-assembly between positive charge for the electrolyte, And here we are studying actually interfacial tension in the system, the complexation strength, the strength of the interaction on the way the polymer correctly self-assemble, and we study also the impact on the local structure typically. And recently we have been using surface tension measurement to actually as a very sensitive tool to follow the mechanism of formation of those packs. And in particular, we are focusing on one particular object in those packs, which are the croissant phase, which is very interesting for many different applications. And we are actually studying the structure inside, how they form, how they can be stabilized, if we can encapsulate things inside. Okay, so but today I will just talk about thin films. So here it's a common slide. I don't think that I need to convince you that organic thin films are everywhere. And so that's the reason why we need somehow to understand how they behave, especially when their thickness is very low. Low meaning that the thickness is comparable to a couple of ranges of duration of the molecule you are using actually. So I would like to start the talk by talking about the pioneering works made pretty much 30 years ago. The first breaking experiment was made by Kelly and Jones. They just measured the glass condition of polystyrene films as a function of the thickness, and basically they observed that indeed the glass condition was actually decreasing with the thickness. And so the idea at that time was that maybe there is a liquid-like layer on top, and this basically was able to reduce the glass condition. Pretty much at the same time, Gunther Reiter, that you know, he made also a very interesting experiment using sphere reflectivity. And in his experiment, he showed that basically when the polymer layer is confined within a couple of ranges of regeneration, the density near the substrate is changing. So the picture that people started to have at that time is that probably the effect on polymer film is a double effect. There is an interaction with the substrate and the presence of the free layer on top. So at the end, basically, the reduction in size plus interfacial forces changes sometimes the way the polymer chain can pack or even entangle, and giving rise to sometimes properties that are basically quite different than their bulk counterpart. So maybe I can change. Can you see it? So since then, people have been working a lot and trying to look at different properties. Obviously, the glass condition, also the viscosity in thin films, obviously the chain conformation, the stability of those films, the physical aging, the way we make them also is very important, and also the density. This is more recent, but people are focusing on that. And if I wrap up a bit, since then, this is my understanding, my feeling is that since the pioneering work, the literature has gone crazy, really, because it's really, for me, it's the endless source of publication, disputes and opposing results. People are basically arguing all the time. I mean, one of the explanation is obviously that the processing condition people are using might be different over the years, and also especially the probing technique to measure, for example, the glass condition or the density are different, and so at the end it might be opposite results. So now currently, my feeling is that there is no clear consensus on the mechanism that basically generate different properties like the glass transition or even density in thin polymer films. So the question we asked many years ago, it was in fact, does density really vary in polymer films? There was a couple of publications on that topic with obviously opposite results. And so we decided to investigate, in fact, this issue by trying to use or to develop different way of measuring the density. Because the idea was, okay, if the three ways give the same results, we will be confident in the results. So we have developed different methodology. So the first one, actually, this was made by my colleague Guillaume from Lorient the first time. So what he did, basically, it's easy. He encoded polymer films, and he measured basically the refractive index of those films as a function of the thickness. And what he saw that in fact the refractive index did increase quite a lot when the film thickness was very small, up to a value of 1.8 compared to the bulk, which is close to 1.6 basically. The thickness here were actually measured by X-ray reflectivity to be able to decouple from the refractive index, because when the thickness is very small, it's very difficult to compute at the same time both quantities. And so if you believe in the closest-mosophic relationship, you can go from the refractive index to the density quite easily. So in fact, the refractive index increasing means that density should increase within the film. In that experiment, so this is a graph showing basically all the measurements that were done, the ellipsometric measurement translated in mass density using the closest-mosophic relationship, but also some measurement made using the electron density profile, typically that you can extract from an X-ray reflectivity curve. Obviously, this is model dependent, but still. And also, in some cases, when the film is not that small, you can extract directly actually the density, the electronic density of the film directly from the critical wave vector for the polystyrene. So, and here you can see that, I mean, from that experiment, it's obvious that the mass density somehow is increasing quite a lot for polystyrene when the thickness is reduced. But obviously, as many people told us, and it was very complicated to publish and things like that, X-ray reflectivity is a model-dependent type of experiment. Ellipsometry, it's complicated also because you cannot really couple the refractive index and the thickness, especially when you're working below 50 nanometer. And we didn't know really if the closest-mosophic relationship was really valid at that dimension. So we decided to go further and try to push forward something different to assess at least directly that the density was varying in polymer films.
Just a quick question. If you go back to the previous slide.
Yeah.
Like if you extrapolate, you think that if you go to really thin film, your density goes to increase.
Well, I mean, we can still extrapolate, but in practical, making fields below 6 or 7 nanometer, it's complicated for many reasons. But yes, in practical, it should go up. But we never made the experiment, so we don't know. This is typically a parabolic variation. We'll talk about that later on. But yes, this is quite impressive.
Persistence length.
Sorry?
In just remind us of persistence length of the trace. Is it similar to 20 nanometers or is it larger?
The persistence is smaller than that.
It's smaller.
Yes.
So it's not a similar line.
So we decided to try to think about a new experiment, I mean, a more direct way to probe it without any model dependency. So as Pierre, actually, this is Pierre here. So many years ago, Pierre told you I was working in the Rodia lab in the US, and basically when I first arrived over there, they told me, okay, Rodia is producing producing a lot of building blocks, nanoparticles, block polymers, polyelectrolyte. We should find application for those building blocks. So do it. And so we had on the shelves this sodium oxide nanoparticle. They were used for UV absorption application or the exhaust system because it's a strong catalysis, and also to in chemical mechanical polishing. This is typical the way to polish wafers, simple wafers. They use those guys in fact. And it turned out that I tried to absorb the solution of those guides onto polymer substrate. And you can see here the absorption was quite strong. This is a polystyrene thin films on the wafer covered with nanoparticle easily. You dip it and the absorption is quite great. And if you see here, this is the polystyrene layer without anything, and this is the polystyrene layer with this layer. So you can identify pretty much any polymer. Here, for example, you have a pipette, the pipette that you're using in your lab. If you cover it with monolayer particles, you can see here, barely see, rise into a polyethylene pipette. So meaning that those particles somehow were absorbing on pretty much all the polymers, even Teflon. We did the experiment. So obviously the Teflon was not hydrophilic, but it was less hydrophilic. So meaning that maybe we saw that time that maybe the absorption was somehow governed by maybe the refractive index of the particle. And so we decided to check that and to absorb the sodium oxide nanoparticle on bulk polymer film. Bulk meaning at least 200 nanometer polymer films to see the variation of the absorption as a function of the nature of the polymer and the refractive index of the polymer. And strikingly, what we saw is that the adsorbent amount scale linearly with the refractive index of the polymer you are trying to absorb the particles. So we use two typical techniques to do the absorption: optical reflectometry using a stagnation point, and also the QCM typical setup to measure the absorption accurately. So this is telling us that if we change the refractive index of the polymer surface, we should see somehow a variation in the absorption of the nanoparticle. So actually, if you do a little bit of simple calculation, you can convince yourself, in fact, that if the system is like that in fact the dispersive forces between the particle and the substrate is basically the main component of the absorption. So nanoparticle, at least sodium oxide, absorb mainly through dispersive Ritchie-Van der Waals interaction. This is typical interaction free energy, and this tells you that any increase or decrease in the nanoparticle surface coverage should directly indicate an increase or decrease of the film refractive index. And then relationship. And so actually it's what we did. So instead of generating thick polymer layer, we generated small polymer layer, varying thickness here. So we made the experiment for polystyrene and for PMMA. And we measured the absorption coverage using IFM. So those are the IFM picture. And so the wrap-up is here on the screen. This tells you that the absorption, the coverage of the nanoparticle actually vary exactly in the same way as the ellipsometry measurement that we showed before. Here you see the polystyrene. So when the thickness is very small, the amount of nanoparticle is very high. It's getting higher and higher. And for the PMMA, it's exactly the contrary. So you can imagine that here, PMMA should have a refractive index that actually decreases with the thickness. So here is just some question that some of the reviewers ask us. So what is the influence of the substrate? Obviously, because this is the main concern. And we can see, for example, here you have a system with age-treated silicon wafer without the layer of silicon wafer that people are using all the time. And so here by simulation, you can see that we don't see any effect up to, let's say, 6 nanometers. Below could be complicated to make a difference between the effect of the substrate or the effect of the film. Here is just the same experiment that we saw before. We just made the PMMA films on silicon wafer with or without the silicon dioxide layer, and actually the trend is the same. Okay, so the physical chemistry is not responsible for the nanoparticle coverage. So here, those are the two curves that we did obtain at the end: the NP adsorption that you just saw, and the ellipsometry measurement that we did again, and you see that the two variations are really similar. Obviously, this is an ellipsometry result; it's model dependent, but this guy, this experiment is not model dependent. And, but I agree that here what we see is only the adsorption, and we saw before that this adsorption is related to the variation of the refractive index of the film and then to the density inside. So both results did agree, but again, when we tried to publish, it took us a lot of time. People were not happy at all. I remember a guy that told us one sentence: "I don't believe it." Stops. And okay, but at the end we were able to publish it, but it was still not satisfactory. So we decided to think about the system to prove that the system was directly increased or decreased with the thickness. So as you can see here, the dashed curve, this is could be an hyperbolic variation of the refractive index as a function of the thickness. So this was our main hypothesis. So here, this is typical. So if it's a hyperbolic variation, the density of the thin films somehow is a function of the bulk density plus or minus something over the thickness. So if you multiply the thickness on both sides, what you get actually is the mass by unit surface. And this is something that we can normally measure using QCM, the quartz crystal microbalance. So it's exactly what we did. So the way we did the experiment is the following. We did spin coating PS or PMMA on the quartz sensor with the thickness H2. We put it in the QCM. We actually use toluene because it's a very good solvent of both actually polymers. And basically what we did is that we did dissolve the layer completely. So after, let's say after 6 or 7 hours, all the films was removed, not completely because there is always a very small layer that we call irreversible layer that is always absorbed. And this layer is between, let's say, around 1 nanometer. And so here you have a typical QCM signature. So you have toluene. So you have a decrease in the frequency. This is typically due to the swelling. And after a couple of minutes, you see the dissolution of the film. And at the end, it's constant. You don't have anything anymore on the surface. So you have obviously to take into account, well, it's not a big deal, the fact that when you enter toluene into the QCM setup, you go from air to toluene, and going from air to toluene, you have to take into account the fact that the density of the liquid and the medium is changing, the viscosity is changing, and so you have also a drop in the frequency. But if you combine both, actually at the end, you could access directly from those experiments to the density variation in thin films directly. So before going to small thickness, we checked that our approach was okay for a thick layer. So we did it, and we were able actually to retrieve the bulk density of the film that we were spin coating on the QCM sensor. So PS, PMMA, and alpha-methyl polystyrene. With this QCM approach, we were able to basically get back to the real density of the polymer in bulk. So we were quite happy with this result. And so afterwards, we decided to go to thin films to see what we will get actually. And this is the wrap up. It took us a lot of time, but here you can see the variation of the PS density on the left and on the PMMA density on the right, using QCM approach. And what you see basically, it's exactly what we saw with ellipsometry. This is what we saw with nanoparticle adsorption, but in a direct way. So here what we say is that when we decrease the thickness of the polystyrene, the density can increase quite a lot, meaning up to 40–50%. I agree that the value, the absolute value, is maybe a bit difficult to understand, but at least the variation, it's obvious here. We were also able, from those data, to retrieve again, once again, the density, the bulk density using the same approach. So everything was somehow consistent here. So mass density does strongly vary with thickness, at least from the QCM.
Jean-Paul.
Yeah.
I'm sorry, maybe I missed something, but so you control the thickness by changing the time of contact with polymer?
Well, actually, no, we are not controlling the thickness, but we are spin coating the film. We are measuring the thickness of the film, spin coated. So we have the thickness of the film. We put it in the QCM with toluene. Toluene dissolve everything.
Okay. So you control the thickness at the beginning.
At the beginning, yeah, obviously, otherwise you cannot access to it.
Any measure it by this time?
We are measuring with ellipsometry, X-ray, and IFM to triple check, I would say. And at the end, it's what we got.
The vertical axis, what is it there precisely? Is it really density, or is it the total mass per unit surface?
It's
not the same
it's
thing.
the mass, yeah. I mean, it's the mass per unit surface that we call density. We have, let's say, we have a thickness, and we know exactly what we have the mass inside, so we are able to derive a density. We call it density. Yeah.
You deposit the film directly to the quartz.
Yeah. That's why it was a bit tricky, but yes, we still coat the film directly on the quartz sensor, and after we put it in the PCM, and we dissolve it to be able to measure actually the film, the amount. Let's say it's an average. It's an average. Obviously, everything here is an average. Maybe closer to the substrate is different, but it's an average. Yeah.
Imagine that you have the same density in the bottom, right?
Which one?
The density that you are measuring for the value, the absolute value. What pressure would correspond?
The pressure, you mean what?
If you measure at ambient pressure, ambient conditions, you have to keep the polymer density.
Yeah.
Now assume that you have the value of 1.5 for this time.
Well, I'm not assuming. I'm just saying here that it's varied in that direction. And I agree with you that it's kind of surprising.
Would correspond to enormous pressure.
Yes, but
So
frankly speaking, I don't.
So what's your microscopic?
My understanding here is that well, maybe there is another slide afterwards that maybe can help us to understand. I mean, at least me. But it's not over yet. I will come back to the explanation if I am able. But okay, so we were quite happy with that, and actually during the former years, in 2020 during the lockdown, a nice guy, Samuel Wood, he was a postdoc in the group of Whiteside in Harvard. he contacted us because actually he developed at the same time another way to measure the density in thin films using magnetic levitation. And actually, each time he went to conferences, it was horrible for him because people basically were not very happy with that. So we checked together a lot, and actually he was able here to see the result using the magnetic levitation. He was able actually to find exactly what we find in the past. And actually in that publication here, we put also our results. And you see here, so those are the 4 results over the years: ellipsometry and XRR, nanoparticle absorption, QCM, and magnetic levitation.
But here in this experiment, there's no substrate, right? It's a 3D floating film.
Well, actually, there is a substrate at the beginning because they have to make. So actually, they are using. They are spin coating a layer of polystyrene on top of a small layer of PMMA, polymeric acid, deposited on the wafer, and you put it here inside the machine with the liquid, the dilated liquid, and so the film will float off quickly, and after the film will basically fly around in the fluid, and the height will correspond to the density that they are able to calibrate for with bits of known density.
Do they allow in the experiment the film to equilibrate to the extent that it forgets where it came from? Because if it has, we're showing that there's a strong impact of that layer close to the interface, close to the substrate, if it takes a very long time to forget about this initial absorption. So perhaps it has residues.
Yeah, that's a good point. I didn't do the experiment myself. I read the paper many times, but he didn't mention that. The only thing that I know is that as we did, we relaxed the chains by heating close to the dissolution. We remove any trace of solvent. We release any stress that were inside, and after we do the measurement. In this case, frankly, I cannot answer your question. So we are quite happy because 4 approaches were basically leading to the same conclusion that density might vary in polymer films, for polystyrene increasing a lot and PMMA increasing a lot. So if you are not convinced, this is a very, very, very clever experiment that someone did. He simply actually spin-coated the film, floated it off, and put it in a glycerol liquid. Glycerol has a density which is 1.25. He made thick and thin films, and he let the system for many hours. And at the end, the small films was going down, and the thick film was going down. So I mean, for me, it's a direct proof of the fact that the 2 films, they have different density, and that the small films has a density that is higher than the glycerol side.
Jean-Paul?
Yes.
Can you explain why you have a gradient of density inside this experiment?
What do you mean?
Because this is all based on the fact that you impose a gradient in density inside your magnetic.
No, this is. I mean, you can do it here in your on your bench. You're just taking glycerol and you put the film inside. That's all. There is no magnetic force, nothing inside. Actually, at the beginning, I talked to you about Flavia that was working on other topics, block copolymer absorption, and if we make a bilayer, if we absorb a block copolymer to make a brush, not dense brush, but a brush of block copolymer on substrate for wafer, and if we measure by IFM in an organic solvent, the surface is smooth and nice as expected. If you remove the solvent, what you see is that something that I call an organized inorganic wetting, something that was already seen many, many years ago. So you have a bumpy structure. And this bumpy structure is polystyrene here, okay? And so if you, what we did is that we measured the mass or the density, if you want, absorbed here using QCM and also from IFM imaging. So we were able to count the number of blobs to measure the volume. And to make the two experiments okay together, we had to put inside a value of density above 1.3. So this was just another evidence for us that somehow polystyrene, when it's confined, the density seems to be higher. Okay, but I agree that this was the big question in physical density value for polystyrene. Many people told us that. I cannot really answer, but if you think about polymer in the bulk, yes, you're right, it's impossible. But if you think that the polymer is confined and interacts strongly with an interface, you can imagine that somehow the polymer can pack a way to increase its local density. So
some of what I'm worried is that has to do somehow with the definition of the width of the film. Then you never measure actually local density within the layer. You measure a cumulative effect.
yes,
Over, you integrate an effect over the full layer.
yes,
Yeah. So it must somehow, so it's somehow related to total material absorbed on the material divided by the volume, which is the surface, plus H. So your definition of H must somehow enter here. Suppose now this effect you get a reasonable measure for H, but for using this H value to calculate the density,
yeah,
you get the same to high value of H, by a few percent. This you can see for densities. For density, it looks dramatic, while for H, it doesn't look dramatic at all.
yeah.
So effectively, you use an H value to give us values of density in gram per volume.
Yeah.
And I think that is the thing we have somehow to be relaxed about that. Yeah. So it's maybe you have to normalize your H value, and then you get a different value for density.
That's a good point, maybe.
But I
But
don't
how could
understand
you?
where the H value enters. Yeah. You plot as density divided as a function of H. Somehow in your calculation for the density, you've used the H value.
So why not trying to do it? I'm a physical chemist, so nobody's perfect. But I understand completely what you say. But how do you explain the experiment with glycerol?
Yeah, there I'm not completely sure what you should for the glycerol, for instance. If you have the thin film,
Yeah.
wouldn't the thin film, the glycerol, will not stay a thin film? I would imagine that.
At the end, it's still a thin film. I mean, it's still floating around.
As a thin film, is it not?
Oh, you mean
You cannot
folded?
really see if
Folded.
it's not folded, but
You
it's
folded.
twice the film thickness.
Yeah, I mean,
And therefore you can, if your argument carried over, it should be the unique function of film thickness. As soon as the film folds up, something like that, it's twice the film thickness.
yeah, I agree, but
3 times and so
I
on.
don't think
So
so.
this argument is intriguing,
Yeah.
but I don't think it's completely.
Yeah, I know, because those results is kind of freaky because I completely agree with you, but the fact is that we got the result that we got. Maybe the interpretation was not correct, but with 3 different ways of doing it it started to be a lot. But maybe you can help me.
We are not opposed to the ideas of density method changes a function of H. The trouble is also if it agrees that H enters in the calculated mass density.
Yeah.
Suppose now that the functions of application purposes, this density profile which I have measured is more or less abrupt. Yeah. So the definition of H might just change because H depending on how you measure it, that the tail of the distribution matters. Yeah. So
that's a discussion after.
Yeah. If you have time, I can drop by. That would be interesting for me. So this was just quickly to say that we went into the literature to see what people were using molecular dynamics simulation make measurement. And here you have 3 different papers showing that when polystyrene is confined with a strong interaction with the underlying substrate, they can measure obviously the variation of density, but also they can measure values that are very high, close to the substrate. Meaning that those values, yes.
This must be angstroms. This cannot be restricted. I have to pay by actually. This must be angstroms.
You mean here?
Yes.
Yeah, I mean,
this is only the very first molecular layer, which has
yeah. Are you sure?
Yes, I'm sure.
I took it from the paper.
I have to pay by.
Okay, so it's angstrom?
Yes.
Okay, great.
Okay. It's comparable.
Yeah, it's angstrom. You're right. So here we cannot see it because there is, but here it's also angstrom. But what I'm saying is that the value here, they are able to find very high value. I agree that it's more close to the interface, but at least here they find something related to that. And the explanation that because of the interaction, the polymer can be somehow packed or layered, and this is giving rise to somehow higher density. So I will not argue with higher density. I will just argue with the variation of density, which is more easy to struggle with. Obviously, when you think about density, people are working polystyrene or PMMA, they have measured glass transition. And what people are finding all the time is that the glass transition of polystyrene decreases when the thickness decreases, and for PMMA it's the contrary. So how can we rationalize actually those results with the fact that the density is increasing for PS and the glass transition is decreasing? It's something that is difficult to understand. Because usually the glass transition, at least in the papers, is ascribed to an increase in the free volume. Okay, it's at least the way people are explaining the decrease of the glass transition of polystyrene with the thickness. But in fact, I mean, this is right. But in fact, the density of the free volume, the density in free volume somehow is related, of the film that we are measuring at room temperature, 20 degrees, is in no way predictive of their variation in temperature. Okay? So it's not because the density at 20 degrees is 1.3 that close to the glass emission, the free volume will be different. So what we did is what a lot of people did in the past and even now. We are measuring the coefficient of thermal expansion. Okay, so we spin coated the polystyrene film, PMMA film, and we, as a function of the thickness, we made a ramp. So when you increase the temperature, it's a linear variation below the glass condition, also above, and there is a kink, and the kink is the glass condition. So we are able basically to measure the coefficient of thermal expansion. And if you plot it as a function of the thickness, this is what we did. And we also put in those graphs, actually, the data coming from all the people in the literature. So what you see here is that the CTE, variation with the film thickness appears to be opposite for PMMA and PS, exactly at the density for PS and PMMA are opposite. And they are varying in the very same manner. Okay? So obviously, CTA is not free volume. It's related, but it's not really the measure of the free volume. So we went into the literature as well, and we found a couple of experiments, but this one is a nice one, where people were measuring actually the free volume using annihilation lifetime spectroscopy. Positron annihilation lifetime is something that is typical for that. And what you see here is that, first of all, the free volume at room temperature here, for example, is smaller in the 22 nanometer film than in the bulky film. It's like here, you can see there is a big difference. What is more important is that the free volume in the very small film increases with temperature much faster than the thicker one. You see the slope here? And so the measure of the blast transition associated with the two free volume, the two thickness, is 84 for the small one and 100 degree for the second one. So this means that actually the way we understand our result, especially the density result, that the critical free volume V is reached at a lower temperature for PS film than for PMMA film, due to a higher or lower CTA, resulting in a higher PMMA or slower TG for PS. And so somehow you can make the two results somehow compatible. So an increase of density in PS appears then compatible with a TG decrease for the same PS. And this is also true for PMMA. A decrease of density of PMMA, when you decrease the thickness, appear then compatible, at least to our eyes, with a TG increase for PMMA. So this is just the end. I understand that those results are a bit intriguing, but I mean, so to wrap up, we put forward with my colleague different methods with different physical grounds to assess or to measure directly or indirectly polymer density in thin polymer films, or something that we think is polymer density. So 4 techniques just mentioned. The striking result is that the density varies for both polymers. The glassy one we never tried with other, and the PS and PMMA, the density varies in opposite way, like this graph. The unphysical density that people are seeing in our result, I mean, appear at least in the, I mean, they are likely supported by some simulation. I'm not saying that they are 100% supported, but what we see is that very high density are possible when the polymer is confined and when the interaction between the polymer and the surface is very high, at least on few functions. And we were able actually to correlate the glass transition and the mass density through the measurement of the process. Okay, so just I would like to thank actually my co-workers. As I told you, we made it over the years without any funding. So this is a PhD student that was working on something completely different, but she took a little bit of her time to do some measurement, and also with Joanna, my co-worker in CRPP, and also to some other groups. Thank you for attention, and if you have more questions, I will try to answer.
Thank you very much for this interesting talk. Maybe I'm a simulator myself, and I would say simulations do not support such density variation. I mean, one sees in the simulations always the first peak, but this is one molecular layer, which has a different packing. This cannot explain the different density for several nanometers.
I agree with that.
If you average that, this cannot.
Yeah.
And for all my feeling from simulation, I mean, in the picture, what can change the density when you improve the packing? Crystallization, for example, makes you change the density up to 20%.
Okay.
And I think here you stay amorphous.
30.
Or maybe 30, but that's really generally the maximum. And I don't see that in an amorphous system you can have 50% or more density change.
This is
so there must be something in the analysis, some nonlinear effects which may be dropped in. That's what you calculate as a density is not a real density, but there is some dark matter hidden somewhere, which you have to find in the.
That's probably why I'm here, but I understand what you're saying. I put the slide with molecular dynamics not to say that it supports the variation, or just that sometimes it's possible to have very high value. And I said when we are very close to the surface, I agree with this, just over a couple of microns.
Just one molecular.
Yes. What I can say also is that the variation is obvious. There is a variation. I agree with you that close to when the film is very small, the value is very high, and we don't know really if it's possible 20, 30, 40. If those are really true. The only thing that I can say is that we made different experiments with different physical probes, and we found always the same trend. And this guy, but I agree, I understand your argument with the flying thin films in the glycerol. I have seen movies of that. Not sure that it was solved, but maybe there is something to dig to understand why this guy is actually finding.
The following cannot explain. It must absorb something else. I don't know what is flowing.
Yeah, I mean, this was not, we were not able to discuss that issue, but okay.
Thank you. I do have two questions.
They are nice.
First one, in your result, when you take into account I guess that you take into account the sources of the substrate to reflective measurements, but then when you switch to ellipsometry, you cannot do that. So how do you expect that the roughness might impact the measurement?
Roughness is one of the dependent tools, and I agree that actually
because it's the same order of magnitude as the
yeah. And what is right is that I mentioned the reversible layer. When you actually spin coat any polymer layer on substrate, and after you dissolve that, you always have this irreversible layer. So if you increase the roughness of the substrate a little bit, actually this irreversible layer is thicker, because actually the macromolecule entropy cope better with the roughness than with the. So I'm saying that because in fact that I agree that with the roughness we didn't pay much attention to that. The only thing that we did is that with the selectivity, if you're measuring the when you see the, I don't know if yes. So those are typical exterior of the polystyrene. So those are the reflective curve. So here you can see you have the critical wavelength vector for polystyrene, and you can see by eyes. And actually, from theory, you can actually access the electronic density directly from the position. So you don't need any model, and but you cannot do it when the thickness is very small because you cannot see anymore the critical. What I'm saying here is that at least for the thickness above 20 nanometer, we were able to directly measure electronic density that was higher and higher with the thickness. That's. But I agree that actually we would like to actually make rougher substrate to see the influence in the actual density.
Yeah, and my second question was about the difference between the PMMA and the PS.
Yes.
Do you think that it might have of origins the type of bond in the crystal that might be hydrogen bonds again hydrophobic or whatever the PS?
Yeah. Well, this is a more general question that people for PMMA people were using wafers with silicon dioxide layer, and depending on the tacticity of the PMMA, they were able to generate hydrogen bond interaction between the silanol, the silicon dioxide, and the backbone. That's why, that's how they explain this increase in the glass condition. And here we see exactly the contrary. And the way I see it is that the interaction, the change it's absorbing, okay, it sticks directly on one of the sides on the substrate. So somehow it's frozen, it's out of equilibrium, so the number of conformation is not possible, and so density is small. That's how I see the variation in density problem. But I mentioned at the beginning with the nanoparticle experiment, we did it also for PMMA on silicon wafer with the dioxide layer and without. And the result was the same. So I'm not completely
I'm always surprised about these experiments that they're always done on a solid surface because you can imagine that this has quite a lot of impact. I'm not very familiar with the literature, but do people try on liquid surface, for example, so that the chains can be like small?
yeah, they're made of standard. Yeah. And obviously the presence of two free interface is changing a bit the story. But actually we made it using substrate because in the literature people started to use substrate, and we wanted actually to see if we were able to have different results or not. But why not?
Do people find different results, or do the results agree between the different types?
At least for substrate on substrate, with ellipsometry, people can find opposite results. Really. Just because the way you treat the data can influence a lot, the way you prepare the sample, the way you anneal the stuff. For the nanoparticle absorption, we were the first to put forward that, in QCM as well. So, but in the literature, people disagree with the increase or agree with the increase of the density. A little bit like the glass condition. So for the moment, it's not clear. The trend is not clear, but from what we did with 4 different approaches, for us at least, the trend is clear. The only thing that is still puzzling is the absolute value of the density for polystyrene. I agree that this is still, so maybe there is something to understand, and we have to talk with clever people.
That's why you are here.
Yes.
Other more questions? Good one more.
I was quite impressed by the size range of the 40 nanometers. Huge.
You mean huge?
When you start to see a difference in the density. Polystyrene, people work on polystyrene nanoparticles. Do people look at the densities of those nanoparticles? In principle, you could maybe this could be a nice experiment where you don't have a problem with the surface.
Yes, actually, the problem is that there are a lot of things different inside due to polymerization, initiator, things like that. But I should admit that we didn't find any body that thought about measuring the density of polystyrene. Maybe there are, but we are not aware. But yes, it's probably a good point. But again, to be sure that it's really polystyrene, after we have to anneal to release any stress. The problem with polystyrene is that most of the nanoparticles are cross-linked because they are used in different applications, and if you have a little bit of solvent, they are not cross-linked. So cross-linking them obviously will change the result. But making nanoprecipitation maybe of polystyrene droplet using Rousseau, for example, the Rousseau effect might be a way to after trying to measure the density of those nanoparticles.
Okay. I see no more.
I have more.
Yeah, well, maybe we close the session and we can continue
Yeah, yeah.
discussing in private afterwards. So thank you very much for these intriguing experiments.